So now this video discusses about what we call as the actually periodical trends, or we call them as the periodic variations. So we understand that elements are classified as the representative elements. We have the transition metals, we have the noble gases, and there are some other actually classifications. And apart from that, the elements are said to be in a different groups. We have group 1 elements, and we have group 2 elements, 3, 4, and so forth. And these actually elements in their respective groups, they portray the same physical characteristics as well as the chemical characteristics. But now, apart from this, we also have what we call them as the physical trends, in which these actual elements portrays across or on the whole entire actually a periodic table. So our interest is to look at the physical trends in which these elements do portrays when we are looking at the periodic table, and we call them as the physical trends or physical variations that we are to look up to. But now we have what we call it as the should be the effective nuclear charge. We'll be talking about the effective nuclear charge as the physical variation or the physical trend. Effective nuclear charge. We'll be talking about the effective nuclear charge and in the discussions. And I will also have what we call as the electron affinity. We'll be talking about what is electron affinity all about, but you should have to get that on. And we'll be talking about what we call as the ionic radius. So we'll be looking what is ionic radius all about. So just have to be there as well. And I'll be looking at what we call as the atomic actual radius. We'll be able to understand what is atomic radius at the end of the day, but just have to be there as well. And I'll be looking at what we call as the electron affinity. This should be electronegativity, rather should be electronegativity. So electronegativity, we'll be able to understand what is electronegativity, and we should also have to understand about what we call as the ionization energy. Okay, we should have to understand what we call as the ionization energy. So we'll be able to get up to what is ionization energy at the end of the day. And these are the actually physical trends that you should have to understand, on the periodic table. We have the effective nuclear charge, electron affinity, ionic radius, and we have the atomic radius, electronegativity, as well as the ionization energy. So let's start with actually effective nuclear charge. Now, what is the effective nuclear charge? If we say a nuclear charge, and by the way, if we are to look at the atomic structure, let's say we have a lithium ion, it should be lithium atom. A lithium atom is said to be having 3 electrons, is said to have the atomic number as 3. It means it is having 3 electrons. And how are these electrons distributed? And according to the components of the atomic structure, at the center we have the protons that are positively charged, and we have the neutron with no charge. And outside the nucleus contains the shells. We have the first energy level, that contains 2 electrons. Now that is according to the configuration using KLMN notation. And we have the another energy level, which is the second energy level, that must have 8 electrons. But now, since we are remaining with a single electron, we'll have it as that. So this is atomic structure of the lithium atom. Now, if we say a nuclear charge, it means a proton charge which is inside the nucleus. That is what we call as the nuclear charge. Now, if we are saying effective nuclear charge, it means this is the net positive charge available for the this is the net positive charge available in order to attract, this is the net positive charge available in order to attract electrons in the in a given energy level. That is what we call as the effective nuclear charge. This is a positive charge available for the attraction of the actual electrons in a specific energy level by considering the shielding effect by the other electrons. That is what we call as the effective nuclear charge. This is a positive charges. These are the positive charges, or can be the positive charge available to attract, the electrons in a given energy level by considering the other actually electrons in a core shells that are shielding that particular electrons in that energy level. And for instance, you just have to understand that this outermost shell electron is being shielded away by these actually inner core electrons. But at the end of the day, this electron is still experiencing the force towards the center because of the actually a net positive charge from the center, which is a proton. How can we be able to determine the net charge from the center, which is responsible for the attraction of this towards the center? So now that's what we call it as the SEF. That is the effective nuclear charge. We present it as a SEF. We present that as a SEF. That is effective nuclear charge. Is given as the proton number, which is given as Z, and minus S. S corresponds to the actual screening effect or the shielding effect. In other words, these are the number of electrons. These are the number of actually inner core electrons that are shielding the electrons of the given energy level. For instance, we have this is a lithium with a proton number given as 3. And what are the electrons that are shielding this outermost shell electron? We have these 2 electrons. Therefore, we'll have it as 2. So now the Z will be given as +1. So it means the only actually a proton charge which is responsible to attract the outermost shell electron is +2. That's what we call as the ZEF. That is the effective nuclear charge, or the net actually a proton charge responsible to attract the outermost shell electron. That is. And let's consider, let's say for instance, we have a chlorine. A chlorine is said to be having 17 electrons. It has the atomic number of 17. It should be 17. And let's think of having its actually atomic structure. Now the atomic structure is given as, this is a proton charge and this is the neutron. And we can have, let's say, the first shell must have, 2 electrons. You should have to understand about the configuration using KLMN notation. And the second shell must have 8 electrons. So we can have 8 electrons in the actually a second shell. So these are the 8 electrons. And in the third shell we have about 18 electrons. But now since we are having insufficient actually electrons remaining, then now instead of having 18 electrons, we'll have 7 electrons. Therefore have 7 electrons here. So this is the atomic structure of actually a chlorine. But now how can you be able to have the effective actually nuclear charge of, let's say, electrons in the outermost shell of should be a chlorine? Now the point of interest is the ZEF, which is the effective nuclear charge, is given as the proton number minus the inner core electrons that are shielding the electrons in that particular energy. For instance, we'll be looking at the inner core electrons as those in the first shell as well as the actually second shell, because are the ones that are shielding the outermost shell electrons. That we can have it as should be given as S. And the proton number is given as 17, and how many electrons are actually shielding? How many electrons are shielding the outermost shell electrons? We have them as 10 electrons. So therefore, the effective nuclear charge of the outermost shell electrons of a chlorine will be given as +7. So which means this corresponds to the amount of positive charges available in order to attract outermost shell electrons towards the center of a nucleus. So that's how you should have to understand that one. And how about the effective nuclear charge, and let's say for the electrons in the second energy level? So what did you say? Principle remains the same. And on this case, it means what you can have is that of, and there should be, by the way, you should have the same S here, and I have the atomic number of 17, that is a proton number, and how many electrons are shielding the second shell electrons? We have 2 electrons. So in that case, we have the ZeF being given as +15. Now you should have to understand that as we go actually towards the center, as we go towards the center, I should say, as the number of shells are increasing, as we move away from the center of the as we move away from the center of an atom, number of shells increases. As the number of shells increases, it means a ZeF also decreases, because the force of attraction in which the electrons experiences towards the center keeps on decreasing, and that force of attraction is expressed in terms of ZeF. In other words, when you look at the value of the ZeF, you should have to understand that it portrays the force of attraction in which actually outermost shell electrons has to experience towards the center, and that force is expressed in terms of the effective nuclear charge, or the amount of a proton's charge available to actually basically amount of charges available to attract the electrons in that particular energy level. So that's how you start to understand that one. Now on the periodic table, there is a trend that portrays the effective nuclear charge. And let's consider this is a typical periodic table you should have to understand. Now, across the period, let's say from left to right, let's say that is the case, effective nuclear charge increases. On the periodic table, as we move from left to right, effective nuclear charge increases. So why do you think effective nuclear charge increases? Electrons, as we move across the period from left to right, electrons in the same actually a period, they have the same actually number of shells. But now as we move at each and every point, there is addition of the protons. Now since there is addition of the protons, it means there is an increase in the effective nuclear charge. And for instance, let's consider this case. And for the sake of interest, let's consider the foreign electrons, actually foreign elements, being in the same period. We have, let's say, lithium having 3 electrons, and we have barium having 4 electrons, and we have boron having 5 electrons, and these electrons are in the same period. And we have a carbon having 6 electrons, and we have nitrogen having 7 electrons, and we have oxygen having, should be that of atomic number of 8. Now let's consider to have the ZeF of this, and we should have to appreciate. And by the way, these elements are in the same period. That is like that. And now let's have the ZeF for the lithium. So what is the ZeF for lithium? So the ZeF will be given as, we have a proton number which is 3, and minus how many electrons are shielding the outermost shell electrons. We have 2. Therefore ZeF is given as a positive 1. It means there is only actually a 1 proton charge responsible to attract the outermost shell electrons. And how about the ZeF for barium? Now the ZeF for barium has to be given as, what is the proton number for the barium? We have it as a 4. And mind you, atomic number is the same as the proton number. And minus how many electrons are shielding the inner core, how many electrons are shielding the outermost shell electrons. And for barium, we have 2 electrons in the outermost shell and 2 electrons in the inner core, in the inner core shell. Now for that case, we have it as 2. Therefore, we have plus 2. So that means we have 2 electrons responsible for the responsible to attract the outermost shell electrons towards the center. And how about the ZeF for barium? No, ZeF for barium will be given as, and what is the atomic number for ZeF? We have it as, should be 5 as the proton number, and the minus, how many electrons are shielding the outermost shell electrons? We have them as 2 electrons. Now for that case, we can have it as, should be 3. So as you can see, across the period from left to right, ZeF increases, and that corresponds to the increase in the force of attraction in which the outermost shell electrons experiences towards the center. So that's how we can have it. So across the period, ZeF increases, thereby the outermost shell electrons experiences the greatest force towards the center. So that is how you used to have that one. How about as we move down, as we go down the group? Now as we go down the group, let's say we have the elements in the same group, and for instance we should have the lithium. We have lithium with atomic number of 3, and we have a sodium with atomic number given as 11, and we have a potassium with 19 electrons. And let's say we have that of rubidium, that is Rb, atomic number is given as should be 37. Let's say that is the case. Now as we go down the group, there is an increase in the proton number at each and every point. As you can see here, the proton number is given as 3. Here the proton number is given as should be 11. Here is given as 19. Here is given as 37. So the increase in the proton number corresponds to the increase in the ZeF. So that's how you should have to understand that one. So although actually a ZeF is increasing, but you notice that there is also increase in the number of shells. You should have that one. While across the period ZeF increases, but number of shells remains the same, since number of shells portrays the period in which particular element belongs to. So that is how you start to understand the ZeF. And now let's consider, let's say we have a sodium, and we have, let's say, a magnesium. So which active element is having the greatest ZeF? Which one is having actually a smaller ZeF, or which one is having the large ZeF? For instance, these active elements are in the same group, should be in the same period, and as we go across the period, we are having sodium before actually magnesium. Hence magnesium is having larger ZeF than sodium. So magnesium is having more effective nuclear charge than the sodium. And since as we go across the period from left to right, the ZeF increases. And how about, let's say, if we have iron, and let's say if we have, should be that of ruthenium. So which one is having more ZeF here? And for instance, these actually, so make sure you have a periodic table by you. So these electrons should be, these elements are in the same period. So they are in the same period, and of which iron comes first than actually ruthenium. And therefore, as we go down the group, ZeF increases. So therefore, ruthenium is having more ZeF than iron. That is. And how about, let's say if we have aluminium, and let's say we have a silicon. So what did you say about this? So you should have to understand that aluminium is having atomic number of 30, and the silicon is having, should be atomic number 14. And these actually elements are in the same period, but aluminium comes first than silicon. Therefore, silicon is having more ZeF than aluminium, since as we go across the period from left to right, that of the ZeF increases. So mind you, ZeF corresponds to the amount of force in which the outermost shell electrons has to experience towards the center. So that's how you should have that one. And we also have another actually a periodic trend. That is what they call it as, should be atomic radius. So what is the atomic radius? Atomic radius corresponds to the distance from the center of an atom to the outermost shell electrons. And in other words, to outermost shell, that is what they call it as the atomic radius. So that corresponds to the distance, from the center of an atom to the outermost shell. That is what they call it as the atomic radius. And let's say we have, this is a typical actually atomic structure. Let's say this is a typical atomic structure, and this is the center, and let's say these are should be number of shells. Now the distance from the center to the outermost shell, that corresponds to the atomic radius. That's the point of interest. So you should have to understand that the atomic radius increases with the increase, should be atomic radius increases with increase in the number of shells. And also atomic radius is affected by the ZeF. And if, let's say, across the period, on the periodic table, as we move across, across the period from left to right, we know that number of shells remains the same since we are in the same period. But now, since the ZeF is increasing, it means the atomic radius will have to decrease, because a typical actual atom will feel being squeezed because of the increase in the ZeF. So since the atom will be squeezed, it means the atomic radius will be decreased. So mind you, across the period from left to right, the ZeF increases. Now, despite that, there is no increase in the number of shells, but atomic radius will decrease because an atom will be squeezed, thereby decreasing the atomic radius. And whereas we go down the group, atomic radius increases because there is an increase in the number of shells despite the increase in the ZeF. So that's how you should have that. You should have to understand that one. So atomic radius decreases across the period from left to right because of the increase in the ZeF. And despite the increase in despite that the number of shells remains the same, but now the atom will be squeezed, thereby decreasing the radius. And as we go down the group, atomic radius increases because there is an increase in the number of shells despite the increase in the ZeF. So the increase in the number of shells is more effective than the increase in the ZeF. Therefore, atomic radius will have to increase as we go down the group. So now let's have this question. Referring to a periodic table, arrange the following atoms in order of increasing atomic radius. So we have phosphorus. So what is the atomic number of the phosphorus? We have it as a 15. And we have silicon. And what is its atomic number is given as 14. And we have nitrogen, whose atomic number is given as 7. So we should have to look at the one with more number of actually shells. Or else we should have to decide, we should have to think it as if they are in the same period or not. So you observe that a silicon and phosphorus, they are in the same actually a period, and the nitrogen is in the second period. So nitrogen comes first. Let's say we should have a nitrogen here, and we have the silicon as well as the phosphorus just down below the nitrogen. So silicon comes first, and phosphorus comes second. So for this case, you should have to understand that which actual element is having the largest atomic radius. So these two electrons are the one. These two elements are the ones that are having the largest atomic radius, because they all have actually 3 number of shells compared to the actually a nitrogen, which is having 2 number of shells. But now on these two, which one is having the largest actually atomic radius? The one which is having the largest atomic radius, it's a silicon, because these two, since they are in the same period, but now as we go across the period from left to right, there is increase in the Z, thereby decreasing the atomic radius. So for this case, the silicon is having the largest atomic radius. Largest atomic radius. So largest atomic radius, and followed by a phosphorus. And from phosphorus, that's when we have the nitrogen. So if we are to arrange them in the order of increasing atomic radius, it means we should have to understand that the silicon is having, the largest atomic radius than actually a phosphorus, and the phosphorus is having the nitrogen. That is the order of should be increasing atomic radius, or else you can just have to arrange them in that way. So silicon, phosphorus, and the nitrogen, and have to say they are in increasing order. So keep that in mind. Now let's say this is a typical question. Arrange the following atoms in order of decreasing, should be a radius. Now we should have to arrange them from highest to the lowest. So let's consider each atom separately. And now we have, should be a carbon. A carbon is having the atomic number of 6. And we have lithium, which is having atomic number of 3. And we have barium, and which is having atomic number 4. Now these two actually atoms are in the same period, and by the way, both of them are in the same period. You should have to consider the location of the electron. Actually, you should have to consider the location of the elements on the periodic table, and both they are in the same period. But lithium comes first, then we have barium somewhere, and then we have carbon somewhere. So as we go across the period from left to right, we are increasing Z, thereby decreasing the atomic radius. So therefore, arranging them in the order of decreasing, it means we should have to start with this one, then this one, and finally with this one, because this is an atom with the smallest atomic radius, and followed by this one, and having that one. So that's how you start with. So a carbon is said to be having the smallest atomic radius because it is the one which is experiencing, the largest or the greatest reserve of all these, and followed by this and then this one. And we also have another trend, which is electronegativity. So electronegativity, this is the ability of an electron. This is the ability of an atom to attract the shared electrons towards itself, That is what we call as the electronic dividend. And basically, let's say if we have let's say if we have the nonmetals, let's think of having, let's say, hydrogen, and let's say should be oxygen. Now these two actually elements, they have to share electrons for them to react, since they are all said to be the nonmetals. Now on the shared electrons, we have one atom which is more powerful than the other, and we tend to pull the shared electrons towards itself. That's now what we call as the electronegativity. You know, the ability of an atom to attract the shared electrons towards itself. That is what we call as the electronegativity. And for this case, oxygen is more powerful than hydrogen. Now the shared electrons will be pulled much towards the oxygen than the hydrogen, because oxygen is more electronegative than the hydrogen. Now that's what we call as the electronegativity. And for that case, across the period from left to right, you know, electronegativity increases because there is an increase in the ZEF. So as the ZEF increases, it means the electronegativity also increases as well. And as we go down the group, electronegativity actually decreases because there is increase in the number of shells. As the number of shells increasing, it means the outermost shell electrons will feel the less attractive towards the center. Therefore, there will be decrease in the electronegativity. So keep that in mind. So electronegativity increases across the period from left to right, and that decreases down a group. That's how you should have it. So which means if you, let's say, compare the following, let's compare the electronegativity of the following, elements. Let's say we have aluminium and let's say a silicon. Let's say that is the case. So which active atom is more electronegative here? So these active atoms are in the same period, but aluminium comes first than silicon. Therefore, silicon is more electronegative than aluminium. And let's say if we have the germanium, and we have, should be that of arsenic, should be that. So these actual elements are in the same period, but germanium comes first. So therefore, you know, arsenic is more electronegative than germanium. And how about if they are in the same group? Let's say have oxygen and let's say silicon. So which one is more electronegative? So for this case, you know, oxygen is having less number of shells than phosphorus, actually silicon. Therefore, oxygen is more electronegative than silicon. So therefore, you have to understand that, you know, since this one is having more number of shells, it means the outermost shell electrons experiences, you know, actually, since it is having more number of actually shells, there is a less force of attraction the outermost shell electrons experiences. Hence, it can't actually pull the shared electrons much towards itself. So that's how you should have to understand about the electronegativity as a periodic trend or relationship. And we also have what we call as the electron affinity. Now, if we say electron affinity, this is a bit of an atom to accept an electron. That is what we call as the electron affinity. And basically, this is for nonmetals. Nonmetals are the ones that are more of to accept electrons, and basically from the actually metals. So electron affinity, this is a bit of an atom to accept an electron. And this is also more affected by the ZEV as well as the atomic radius. And for example, as we go across the period from left to right, you know, ZEV happens to increase. You know, ZEV happens to increase. So do we expect electron affinity to increase as well? Now, since the ZEV increases across the period from left to right, we expect that the electron affinity also have to increase. And as we go down the group, because atomic radius is increasing, is actually electron affinity decreases, because the outermost shells tends to be further away from the nucleus. Therefore, outermost shells experiences the less force of attraction towards the center. Therefore, electron affinity decreases as we go down the group, and increases across the period from left to right because of the increase in the ZEF. And let's through more look at some other cases on the same periodic trends. And we also have what we call as the ionization energy. Now this is the energy needed to remove an electron from a gaseous atom. In other words, this is the energy required to remove an atom from the outermost shell of an actually. This is the energy required to remove an electron from the outermost shell. That is what we call as the ionization energy. But before we discuss much about the ionization energy, let's consider, let's say, atomic structure of a barium. So a barium is having 4 electrons. It is having atomic number 4. That is, it is having 4 electrons. And now if we consider its atomic structure, it is having, we have a nucleus at the center, that is, and we have the first energy level that is having 2 electrons. And we have the second energy level that is having also 2 electrons. Now the outermost shell electrons experiences the repulsive force 1 by themselves. This electron experiences the repulsive force by this electron, and also this electron experiences the repulsive force by this electron, and since they are of the right charges. And apart from the repulsive force, these actually electrons exerting towards each other, they also experiences what we call as the shielding effect by the inner core electrons. So which means there are 2 forces that are responsible to shield the force in which the outermost shell electrons, and we have the shielding effect or the repulsive effect by the electrons themselves, and also the shielding effect by the inner core electrons. So that one. So in all cases, outermost shell electrons. So in all cases, the outermost shell electrons experiences the repulsive force by the electrons in that particular energy level themselves, and also by the inner core electrons. Now you observe that it is very easy for a barium to eliminate the single electron, but it will be very difficult to eliminate this electron, because let's say if it is to release the first electron, so amount of energy required to release the first electron is said to be the first ionization energy, whereas the first ionization energy, but it will be less than the energy that is to be required to remove the second one, because this electron experiences the force of repulsive by this electron and by the inner core electrons. Therefore, it will make it easier to be removed. But now the removal of the second actually electron will require more energy. That is now second ionization energy. So you observe that the first ionization energy will be greater than the second energy. Actually, will be less than the second ionization energy. So the reason being, that of, the first actually electron experiences the force of repulsive by the inner core electrons and the another electron in the same energy level. But now the second actual electron will only experiences the repulsive force by the inner core electrons, therefore making it to stromo being pulled towards the center, like that. So the force required to eliminate the second electron, the energy required to eliminate the second electron, is more than the one required to eliminate the first electron, since the only force, since the second electron will experience the greatest force towards the center. So it will need more energy to eliminate that one. So that's what we call as the ionization energy. Energy required to eliminate or of an atom to remove, that of an electron from a gaseous atom. So ionization energy increases as we go across the period from left to right, since the ZF increases. But now it decreases as we go down the group, as I have already put it forward. And we also have another actually a trend, which is the ionic radius. So what is the ionic radius? So ionic radius, I would say it is the opposite of the atomic radius. So ionic radius, it is the radius of an atom. Just have to say it that way. It is a radius of an atom. In other words, it is the distance from the center of an ion to the outermost shell. And for instance, let's say if we have the sodium. By the way, we have two types of ions. We have what we call as the positive ion. That is when an atom has lost electrons. And we have the negative ion. That's when an electron has gained electrons. And for the case of, let's say we have a sodium is said to be having 11 electrons. But now if it is to lose the electrons, let's say we have the atomic structure of the sodium ion. We have the first shell should be a sodium atom, by the way. And the second shell must have 8 electrons. And that will have. And that's now the sodium ion. It should be a sodium atom. And the outermost shell will have the single electron. But now if it is to lose a single electron, which is this? Now it will become the positive ion. And that will have, instead of having 11 electrons, it will have 10 electrons. Therefore, the structure will be like this. So have the structure like this. So just having 2 electrons, it should be 2 shells than 3 shells. So 1, 2, 3, 4, 5, 6, 7, should have 8. Now between the sodium atom as well as the sodium ion, we should do expect to have, the larger atomic actually we should do expect to have the larger actually radius. So in this case, ionic radius should be, in this case, the sodium ion, since it is having less number of shells, it is having, a smaller radius than the atom itself. Therefore, you should have to understand that much as the atomic radius is affected by the ZF as well as the number of shells, and even the ionic radius also be affected in the same way. And also another case is that let's consider the another case. But before we go for that one, you should have to understand that as we go across the period, just like though we discussed about the atomic radius, as we go across the period from left to right, ZF increases, thereby making ionic radius also to increase. Likewise, as we go down the group, since actually a number of shells increases, it means the ionic radius also have to increase as well. So keep that in mind. But now let's consider this kind of a case. Let's say consider the case of the magnesium. Magnesium is said to be having 12 electrons. And let's think of having its atomic structure. Have the first energy level 2 electrons, and the second energy level is having 8 electrons. So it's having 8 electrons. and the third energy level is having, let's say, 2 electrons. Okay, and let's consider the magnesium ion 1 plus should be, let's say, a positive. So it means here, it means magnesium has lost a single electron from the 2 electrons in the outermost shell. Therefore, we have it as this. Let's say we should have that one as this. So which means we can have something like this. Okay, so in this case, what do you think will be the effect on the ionic radius? So now, in this case, this actually magnesium ion should be magnesium atom is having, 3 shells, and also magnesium ion plus 1 is having 3 shells. But now, which one do you expect to have, the larger ionic radius? So which one do you expect to have the larger actual radius between the two? Now you should have to understand that in the case of the magnesium atom, these 2 electrons in the outermost shell, at some point in time, they are able to withstand the force of repulsion by the inner core electrons, and that is making them not to be squeezed much towards the center. Thereby, magnesium ion is actually thereby the magnesium atom, basically it is having larger ionic radius, actually larger radius than this, because now since we only have the single electron in the outermost shell, this electron want to withstand much the pulling force towards the center. Therefore, it will be squeezed more, thereby making the actually radius to decrease. So keep that in mind. And let's consider the case of the, should be, let's say, aluminium. Aluminium is said to be having 13 electrons. And let's consider, let's say, aluminium 1 plus. So aluminium 1 plus, it means it has lost actually a single electron, thereby making thereby it is having 2 electrons in its outermost shell. So 2 electrons in the outermost shell. And how about aluminium, let's say 2 plus? So aluminium 2 plus, it means it has lost 2 electrons in the outermost shell. Thereby, it is having the single electron in its outermost shell. So which one do you expect to have larger ionic radius than the other? And now the one with 2 electrons in its outermost shell. These electrons will be able to withstand a bit the force of repulsive. The force of these actually, I should say, these 2 electrons that are remaining in the outermost shell will be able to withstand the force of repulsive by the inner core electrons. Therefore, this actually ion won't be squeezed much than this one, since we only have the single electron in the outermost shell. Therefore, the one we expect to have the larger radius has to be this one than this one. So that's how you start to understand that one. So now let's consider this kind of equation. For each of the following pairs, indicate which one of the 2 ice species is larger. In A we have nitrogen ion 3 minus, and we have fluorine ion, that is sugar. And as it stands here, we should have to consider that these 2 ions are in the same period. But now nitrogen is having 7 electrons, and the fluorine is said to be having 9 electrons. They have the same active shells. They have the same number of shells. But now so in this case, for the nitrogen, 3 minus corresponds to accepting 3 electrons. And for the fluorine, we know a minus 1 corresponds to accepting 10 electrons. Should be 1 electron, making to be having 10 electrons at the end of the day. And this one also is also having 10 electrons at the end of the day. But now, since they're in the same period, the issues of the ionic radius will be done by looking at the effective nuclear charge. And for this case, actually a fluorine ion is the one with the larger, should be a nitrogen ion is the one with the larger ionic radius than fluorine, because this one experiences the greatest actually effective nuclear charge. So here's just the key for you. When the actual ions are of the atoms of the same period, just have to look at the effective nuclear charge. Just have to look at the effective nuclear charge. When the ions are in the same group, just have to look at the number of shells. When the ions are in the same group, just have to look at the number of shells. And if the ions are of the same active atom, let's say the case of aluminium plus 1, let's say aluminium plus 2, let's say aluminium, let's say plus 3. You just have to look at the number of electrons that are remaining in the outermost shell. The more the number of electrons are in the outermost shell, it means the smaller the ionic radius, if that is the case, because the more number of electrons remaining in the outermost shell, that corresponds to be able to withstand the repulsive force from the that should be able to withstand the repulsive force from the nucleus of an atom, of that particular atom. So keep that in mind. And by the way, let me have a very big correction on this. In fact, you should have to understand that. Let's go on the case of the calcium. A calcium is said to be having 2 electrons in its outermost shell. That is 2 electrons. Now, when we have, let's say, let me go on the, let's say, iron. We have iron is said to be having 3 electrons in its outermost shell. Now let's consider, let's say, iron plus, and let's consider, let's say, iron 2 plus, let's say iron 3 plus. Now on the case of the iron 2 plus and 3 plus, these two ions are having different number of shells. Iron 3 plus, it means it has lost all its outermost shell electrons, and iron 3 actually 2 plus, it means it has lost 2 electrons in its outermost shell, but the number of shells are still being maintained. Hence, for this case, the one with larger ionic radius, it is the one with more number of shells, which is this. But now, how about if we have, let's say, this kind of a case? So in this case, it's true more, these 2 active iron ions are having the same number of shells. But now what they differ is a number of electrons in the outermost shell. And for the first one, it means iron has lost a single electron in its outermost shell. Now it is having 2 electrons remaining. And for this one, it has lost 2 electrons in its outermost shell. It is having now 1 electron in its outermost shell. So which one is having larger ionic radius than the other? Here is where my correction has to be, and disregard. You should have not taken into account. There's something that I've messed up. I've observed that one here. So let's have this correction together. And now for this case, iron actually a positive. It means it has lost a single electron. It is having 2 electrons in its outermost shell. And the iron 2 plus, it has lost 2 electrons. It is having one electron in its outermost shell. So which one do you expect between the one with more number of electrons and which one do you expect with the more number of electrons with in the outermost shell, or with less number of electrons in the outermost shell to have the larger nucleus? The one with more number of electrons in the outermost shell. So the one with more number of electrons in the outermost shell will actually experience, the greatest force of attraction towards the center of an atom, while the one with few number of electrons in the outermost shell, the one with a few number of electrons in the outermost shell, the outermost shell electron want to withstand the force of actually a repulsion by the inner core electrons. Therefore, this one will have larger ionic radius than this one, because because the one with more electrons in the outermost shell will experience more effective nuclear charge than this one. So therefore, this one will have that of larger ionic radius than this. So that's how you start to understand that one. So the one with should be less number of electrons in the outermost shell. The force of repulsive will be greater than this. So that's the correction that I want to expect. That's the correction that I had to give it out in this case. So here is the greatest conclusion. So here is the greatest conclusion. You should have understand that, an ion of the same kind with, more electrons in the outermost shell will have the highest effective nuclear charge, making the whole ion to be squeezed, thereby decreasing the ionic radius. And likewise, the one with should be less number of electrons in the outermost shell will have a larger radius, because the effective nuclear charge won't be greater as we expect in the one with more with the one with more number of electrons. So that's how you start to understand that. And so try to go through those and have up your responses. Thank you.